In this talk, I'll be giving you just a taste of some of the extremely detailed science that JWST will enable in the realm of solar system astronomy. In particular, I'll be focusing on middle and outer solar system minor body populations, and how the information gleaned from JWST will help further our understanding of fundamental aspects of solar system formation and evolution. To start with, I'll give a quick introduction to the relevant asteroid populations. The figure on the left shows a snapshot of the Jupiter-resonant small body populations in orbit. In light green are the Jupiter Trojans, which lie at the 1-to-1 mean motion resonance with Jupiter, and are confined to two extended swarms centered on the L4 and L5 Lagrangian points. Closer in, at the 3-to-2 resonance, are the Hildas, which occupy this peculiar triangular region of space between the orbit of Jupiter and the outer edge of the main asteroid belt. On the right, we can see the large cloud of distant Kuiper Belt objects, or KBOs, in light blue, which are situated beyond the orbit of Neptune. Occasionally, these KBOs are scattered into the giant planet region, at which point they are referred to as Centaurs, and have high eccentricity orbits with dynamical lifetimes on the order of 1 million years. So, why are these widely separated minor body populations important for our understanding of solar system evolution? Recent theories of solar system formation posit that the initial configuration of the outer planets was much more compact than it is today. After the protoplanetary disk dissipated, it is hypothesized that a period of dynamical instability occurred that dramatically altered the orbital architecture of the outer solar system and expanded the ice giants' orbits by disrupting the large reservoir of leftover planetesimals situated farther out. As a result, most of the mass from this region was lost, but a significant fraction remained and became the present-day KBOs. A smaller contingent was scattered inward and captured into resonance by Jupiter, becoming the present-day Trojans and Hildas. It follows that these dynamical instability models predict a common origin for all of the middle and outer solar system minor body populations. And it follows also that a detailed comparison of their observable properties serves as a powerful empirical test of our current understanding of solar system evolution. JWST will usher in a new era of solar system minor body research. The telescope is equipped with 4 instruments providing both imaging and spectroscopic capabilities throughout the wavelength range from 1 to 30 microns. In the context of asteroid observations, instruments like NIRSpec and NIRIs are ideally suited for extremely precise measurements of the reflectance spectra, revealing the presence of water ice and key organic compounds that can serve as a calling card for both the formation region and the dynamical evolution of these small bodies. Meanwhile, MIRI will probe the thermal emission from the asteroid's surfaces, revealing intimate details about the silicate composition, grain size, porosity, and other physical properties of the regolith. Some of the largest KBOs have been studied in great detail, none more extensively than Pluto, which was the primary target of the NASA New Horizons flyby mission. These icy dwarf planets are each unique objects with complex geography and compositional diversity, as illustrated by this vivid image of Pluto's mottled surface. During the first cycle of JWST observations, almost all of the 10 biggest KBOs will be observed as part of guaranteed time observation programs, including Eris, Haumea, Sedna, and Orcus. The enhanced spectral resolution and sensitivity of JWST will provide exquisite reflectance spectra for all of these mysterious worlds, even surpassing the New Horizons instruments in precision. Here we see simulated reflectance spectra for Orcus, demonstrating the ability of NIRSpec to robustly distinguish between various plausible ice combinations. While the complexities of large KBOs are an interesting aspect in and of themselves, these objects do not really represent the overall ensemble properties of KBOs. This is due to their large size, which enables secondary processing of their interiors and regolith through differentiation and surface geology. For probing evolutionary links between the middle and outer solar system minor body populations, our focus now lies with the smaller objects that have diameters less than about 500 kilometers. These primitive objects are expected to be largely unprocessed and therefore are indispensable for assessing commonalities between Trojans and KBOs, as well as studying the effects of space weathering on the more representative sample of icy asteroids. From an observational perspective, Trojans serve as a proxy for the more distant and inaccessible small KBO population, and much interest has been garnered for intensive spectroscopic studies of their surface. NASA recently launched the Lucy spacecraft, which has embarked on a 12-year flyby mission to 5 Trojans in both the leading and trailing swarms. While the in situ observations in the coming decade will unveil the nature of these enigmatic objects in great detail, JWST observations of both Trojans and KBOs will play a crucial role in characterizing their surfaces and helping us place the findings of the Lucy mission in the broader context. One of the most notable properties of Trojans uncovered in the past decade is the stark color bimodality, which separates the Trojans into 2 subpopulations, which I refer to as less red and red here. I've plotted the visible spectral slope distribution of Trojans in green, which was derived from Sloan photometry. This discovery has added an extra dimension to our understanding of Trojan surfaces, and we seek to examine the source of this color bimodality and reconcile our findings with the wider narrative of solar system evolution. Looking now across the other major middle and outer solar system asteroid populations, we find that they too show an analogous color bimodality. While the average colors of the Trojan and Hilda populations are comparable, KBOs have a significantly redder color average, perhaps hinting at the differential effects of space weathering across the middle and outer solar system. The bimodalities seen in all of these populations provide strong preliminary support for a common origin for the Trojans, Hildas, and KBOs. However, further study is warranted. In particular, definitive compositional models derived from spectroscopy are necessary for adequately evaluating possible origin and evolution pathways for these objects. Obtaining high-quality reflectance spectroscopy of Trojans has been a challenging endeavor. This plot here shows the average reflectance of less red and red Trojans from the near UV through 5 microns and is a concatenation of various datasets from both ground and space-based facilities. Immediately, one can observe that the spectra are mostly featureless. In particular, there are no hints of the diagnostic silicate and water ice features that are often detected on main belt asteroids. Meanwhile, recent KL-band spectra from Keck offer the first incontrovertible spectral feature in the form of a peculiar absorption between 3 and 3.5 microns. And this is primarily present on less red objects, as seen here. Looking at this region in more detail, we find that while the morphology of the feature is poorly resolved, the overall shape is reminiscent of some of the rounded 3.1 micron absorption features that we see across the outer main belt. And this is typically interpreted as water frost. Now, other interpretations of this feature include an NH stretch feature from ammoniated clays. At longer wavelengths, we also see hints of weaker absorptions that are analogous to organic features seen on the irregular moons of Saturn. The ammoniated and organic compositional elements here, if proven, would directly point to an outer solar system origin. But of course, higher resolution and higher signal-to-noise reflectance spectra are needed in order to enable decisive compositional modeling of Trojan surfaces. High-quality reflectance spectra of Trojan asteroids using the JWST NIRSpec instrument will definitively characterize the compositional elements that contribute to this 3-micron feature. In this plot, I have simulated KL-band spectra of what we may expect from NIRSpec observations. The simulated data here has exquisite precision, capable of resolving even the finest structure and retrieving definitive molecular and elemental constituents on the surface. It is also worth emphasizing that while the Lucy spacecraft is equipped with a near-infrared spectrograph, similar to what was on New Horizons, the smaller aperture size of the telescope means that the spacecraft data will not achieve nearly the same sensitivity as NIRSpec. In red, I've overplotted the equivalent Lucy uncertainty at the same spectral resolution, which underscores how JWST observations will be indispensable in filling the gaps in data quality that would otherwise limit the explanatory power of the Lucy mission. The 3 to 3.5 micron range is not the only region with potentially interesting spectral features. A recent hypothesis for the Trojan color bimodality suggests that the presence or absence of hydrogen sulfide ice on the surface of progenitor planetesimals may explain the differences in spectral slope that we see today. Laboratory experiments designed to mimic this scenario have revealed a pair of diagnostic absorptions between 4.5 and 5 microns, a region that is inaccessible from the ground and hitherto out of reach of any space-based spectrograph. NIRSpec observations will open up this region of wavelength space for the first time, allowing us to probe these putative absorption features and positive detection of this OCS feature on red Trojans in particular would immediately confirm the presence of sulfur chemistry on the surface and validate the dynamical instability model of solar system evolution. In addition to the NIRSpec reflectance spectroscopy, MIRI thermal emission spectra will provide a complementary view of Trojans and KBOs. Previous low signal-to-noise Spitzer spectra of two large Trojans, Patroclus and Hector, shown here, reveal a broad emissions feature at around 10 microns. This is indicative of fine-grained silicates, similar to analogous structures that we see on icy comets. JWST observations will dramatically improve the sensitivity and wavelength coverage throughout this range, allowing us to model the grain size and regolith properties. Additionally, the recovery of diagnostic features in emission around 50 and 25 microns will yield very tight constraints on the crystalline versus amorphous silicate fraction, as well as the magnesium content of the regolith. Through both GTO and GO programs in Cycle 1, the astronomical community will aggressively leverage the next generation capabilities of JWST to study Trojans, KBOs, and the related Centaur population. Together, these JWST observations represent a giant leap in our understanding of middle and outer solar system minor bodies. By comparing the detailed compositional information gleaned from these programs, we hope to find the smoking gun that will validate or refute our current conception of late-stage solar system evolution. At the same time, these high-quality JWST observations of Trojans and KBOs will be an invaluable asset for past and ongoing spacecraft flyby missions, such as New Horizons and Lucy. Thank you for your attention.